Great.
Righto. Sorry about that, everybody. I don't know what's going on exactly. I got some serious problems with my computer, apparently. Uh, or maybe not so serious. I don't even know. It's terrible. At any rate, we're going to return this over here. Oi. All right, sorry about that, everybody. We have been having some technical issues, and I don't understand why. It's ridiculous. Okay, so anyway, main point of tonight is that we are going to be talking about numerical analysis and being able to solve differential equations, even in the face of awful differential equations.
Yep.
So even if we have something that is not solvable by any means, by any stretch of the imagination, we've tried all the other, efforts that we've seen in the past few weeks. And we just can't come up with anything, then we're still going to be able to, at the very least, get a reasonable approximation for our differential equation solutions. So the example that I'm using, really? Come on, man. Is going to be y prime is equal to 4 minus ty divided by 1 plus y squared, where we want our delta t to be, and we could very well make this variable, but for today's purposes, we're going to stick at 0.1. I'm going to highly recommend that everybody who is interested in this try and create an automated version in whatever programming language you use and see if you get the same results as we get here. And our t0, y0, the initial point that we're going to be looking at for today, is going to be 0, negative 2. Okay. So, let's see. From this point,
I'm going to put this in my plotter as well.
Absolutely.
Just so I have something here, because this is one where you want visuals, I think, to illustrate this method.
Yep.
All right, go ahead. Sorry.
No, that's all right. So from what we have here, what are we going to do to try to figure out where the next location our solution is moving toward is going to be? If I worded that correctly.
Well, so one of the ideas I think this is centered on is that we know the derivative at a point, right? So we have a differential equation, y prime, and if I know a t value and a y value, I can somehow tell what the slope is at that point. And that should give me an idea. If I think back to slope fields for a second, if we had a slope field, we could sort of tell what general direction the next small interval should go in, right? Like what's the slope in that little interval, so that I can draw the next part of the curve, and then maybe take the next part of the curve and draw it from where that last one ended, and then so on and so forth, build a curve that might get sort of close.
Right? So if we go and say like our initial point here was 0, -2, and you said, let's try to find the derivative here. Or we know what the derivative is. What is the slope or the derivative at that particular point?
Oh gosh. Let's see here. So it's 4 over 5. I think that's 4/5. Am I not mistaken? -2 squared is 4, plus 1 is 5. And since t is 0, the numerator will be 4. 4 minus 0 times -2, which is just 0. So my slope is going to be 4/5, which is going to be a positive slope. That's pretty close to 1.
Right.
Something that approaches the line y equals x in slope or something like that.
So for every 1 that we go up, we're going to go 4/5 to the right, and 4/5 is right. That's 0.8. So it is going to be in this direction, but again, fairly small. So I'm just going to do this to get a bearing.
Okay.
And then we can also just go like this. This is a much more accurate version than what I would have done freehand.
Okay. I mean, I don't know if your the whiteboard app has any grid options, but that would be convenient here.
Yeah.
I'm just wondering if that would, just because it would make it more accurate, and because of accuracy, I wonder if...
I don't see one. Oh, I should want to share this here. Hey.
Thanks.
Okay. Yeah, so I don't see a grid option, but
it's fine. I think this will illustrate the point, but
yeah, and like you said, whiteboard was my go-to.
Okay, that's fine.
Back in the day. Yeah, so we got a slope of 4/5. We can make just a arg. Sorry. We can make a tangent curve to the slope at that particular point. And then if we assume that our delta t is going to be 0.1, then we can say, well, we only want this to be accurate to this level of precision. That was probably not the correct word, but anyway. We're going to take this and we're going to continue this line segment up until we get to 0.1. Okay, and then once we get to 0.1, we're just going to
do it again.
Do it again. So now we have to rinse and repeat. The only problem at this point is, what's the y value?
Well, it's wherever we ended off, right? So wherever we left off is going to new y value, and then I just take the slope field and apply that slope wherever we left off and continue.
Right. So then, how far do we actually go?
Well, if you're going 4/5, that's your slope. We'd have to. We need the slope. We need the line through the point 0 to 0, -2, with the slope 4/5. So we could just say y plus 2, or y. I guess the way you're writing it, 4/5 x minus 0. I was making the line, but I guess you got the.
Yeah.
You're filling in the 0.1 for me.
Yeah.
But then
I mean,
-2.
we're just gonna say, sure, we've taken Algebra 1. We know how this works. So.
Okay, I didn't know how detailed you want to go here, but the idea here is you make the slope, the line with the slope 4/5 that goes through the point 0, -2, and then insert our 0.1 there.
Yeah. So we're gonna go with 0.08 minus 2. We get -1.92. So this is going to be a -1.92 in here. And yeah, now we have to just rinse and repeat. So we're going to say again, at this point, we're going to then want our y prime from here. Race Zach.
Erase me. You probably win, actually.
It's all right. I've also got the answers on my other computers.
Yeah, I was gonna say you're probably gonna win on that one. I mean, I have some mental math skills, but I'm okay. I'm a little.
This is also an occasion to pull out the n-simplex pachinko research. So every individual number is going to be squared in its position, because we can turn this into a -1 minus 0.9 minus 0.02 and square that as a trinomial. So this is our three-dimensional simplex, which has coefficients 1, 2, 1, 2, 1, 2. So all of our pure cases, they're all individually getting squared, and it's just one of those. And then all of our cross terms are going to be pick two of them, multiply them together, and that's what we get for our two times that cross term is going to be what we get for each of those individual bits.
Yep.
So we end up with a 1 plus... Oh, no. Oh, man. 0.9 times 2. Man, I was right all. Alright, plus 0.81 plus twice 18 is going to be 0.36, 0.036. Plus 0.0004. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Missing one. And twice. That is 0.04. All right, so 3.6. 646 040004.
I think you just hit an ad break.
Yay. It was because of the restart. Alright, I just checked on my calculator as well as by hand. I did, in fact, get the right value there, so that's 3.6864. Alright, is going to be our y prime for this particular point. That is a fairly significant difference compared to what we had before. Apologies for the ad break, everybody. Haven't got in at the right time either time, so so 3.68. If we're going over 1/10, then we could go up. It's going to be 0.36. Am I going backwards? If we go over 1, we're going to go up 1, 2, 3, somewhere up here. Give or take. It's not awful, but it could work. Alright, and then we fill out this one as well. And again, we need to find the y value here. which again, we're going to use our y prime value and fill in all the blanks. This is going to be y equals 3.6864 times our 0.2. In this case, our new line, right, doesn't actually go through 0 comma anything, so we're going to have to do it maybe a little bit, well, nicer in one sense. We can use the previous value. So this is going to be 0.2 minus 0.1, so our difference in x. And then we're going to subtract 1.92. Apologies, my stuff's in the way. Alright, so y equals, this was 0.1 of a difference, so 0.36864 minus 1.92 is going to be a negative 1.65. What? 6? No. Ah, damn. I'm alright.
You're going, yeah. I think you've
155.
got all these numbers. Yeah, it's that looks about right. 1.56. Yeah, sounds about right.
Yeah. So that's our new y for this one, and that's going to get us this point here. So 0.2 by negative 1.55136. Okay, so who wants to keep going?
By computer?
Right. So the point of this, to do these first couple of steps by hand, is kind of like important to show people, like, this is how it used to be done. This is in fact called Euler's Method, named after Leonhard Euler, who developed this. I mean, it's not like it's particularly difficult and nobody could have figured it out before him, but nonetheless, he was the first one to like really formalize this and say, hey, we can churn this out a lot faster if we don't do all of these individual calculations by hand, or at least, you know, pretend that they're all in isolation from each other. What we want to do is we can say, all right, we're trying to solve for this y that we had down here. So where exactly did that come from? Right, that is, again, our like point slope form that we used here. And if we can call this an iteration, kind of the same way that Isaac Newton did Newton's method, we're going to say that, well, this was, like all this stuff over here, this was y1 that we were finding. So this is y2 that we're finding here. How do we get each of these things? Well, 0.1 was our delta t. 4/5 was our slope, which is the same as f if we define our differential equation, as we had in weeks past. I forgot to do it this time, sorry. If we define our differential equation as f of x comma y, or t comma y in this case, back that up. Right, and then we had our -2 here was plus y0, and our 4/5 was f at x0, y0. That's kind of all crammed in there. We'll spread it out in a second. Okay, and then does that check out when we go back over to our second one? So in order to get our second slope, we plugged in our x1, no, not x, t1 and y1 so close. It's better. Okay. Right, we plugged in our t1, y1 into f for this particular case. And we said that here our 0.2 minus 0.1 is also delta t. And our negative 1.92 is adding y1. So in order to get all of our y sub n plus 1s, we're going to take our f at t sub n, y sub n, multiply it by delta t, and add y sub n. Right, I know I wrote it up there, but write it down here again. So Euler's method says, in order to get our new values, let's take our current location's slope, multiply it by our delta t, and then add our previous y value, and that gets us the exact y value location where we can just get the next one. Okay, so yeah, if we iterate this, this becomes way better and way faster. And we can pop out any one of our good friends. We can pop out with Octave, with Python, with anything that you feel like, right? You can always figure out what your favorite is. So for Octave, which is the same as MATLAB, I'm not wearing my shirt today. That's too bad. Hashtag not sponsored. So first we're going to say we want our t values to go for... You can't see the bottom. Hang on. Oh, no, you can. Okay. We want our t values to go from 0 was our starting value. We did 0.1, and then let's just go to like 2. So that should give us, yep, 1 by 21. So this is going to be all values. T is going to be all values from 0 to 2 inclusive that are come on now. Brain. Incremented. There we go. Incremented by 0.1. If you want, you can also not put the semicolon and actually have it print out to make sure that you're doing what you think you're doing. For the most part, I'm not going to do that. I will silence the input. Silence the output by putting a semicolon there, just because I know what it's going to do, at least in theory. If I screwed up real bad, then oh well. Alright, and then what we can do is say that y, we're going to have that be also a 1 by 21 zeros matrix, which hopefully, yes. Cool. So that's going to match the exact same thing as t. I usually like to set this ahead of time, just to say, like, it needs to be the same size as that other one, and if it's not, then, you know, it's going to break somehow. I just know it. And then in this point, we're going to say that, for I is going to go from 1 to 21. That's not right. don't think it's these. Okay, so for I going from 1 to 21. Okay, so now that we have a little caret on the side that's telling us that we're on an inline portion, so we need to like execute the following. Y of I is going to be equal to make sure I didn't completely mess this up. Okay, hang on. We wanted to find f first. So f being our derivative function. We're going to have this be 4 minus t times y. And for this, we want the particular t and the particular y that we are currently using. I didn't initialize y, because the first one should be a 2. Boo. It'll be alright, we'll fix it. We'll fix it in post. Divided by parentheses 1 plus y of I squared. This should work. Followed after by y of I. It's going to be equal to oh.
What's going on? I'm trying to figure out what the issue here is.
I might have messed up a bit. Let's see.
So you got all the f of i's, and those are going to be the that's our function, is it not?
Yeah.
You programmed in the f of I. That's f of I is going to be your derivative.
Yep.
Okay.
But I think we got a problem here because y sub I is going to be incremented by 1 off.
Mm-hmm. Okay.
Yeah.
So do you need to put a +1 somewhere or a -1?
Yeah, I think so. But then the problem is that if I put a -1, right, it's not going to exist somewhere either at the beginning or the end.
So just initialize a value. I think you could do that. Have like a statement outside your loop that says y0 equals whatever, which is what your initial condition would be, right?
Mm-hmm. Okay, so y sub I plus f, or not sub, but y of I plus f of I times, we're going to need a, right. So I would probably put in an actual variable. For right now, let's just do 0.1 because I didn't do it properly. And then that should be it, right? Because we're just iterating between the two things.
Right. So then you'd have, yeah, that should make sense. That would tell you the next y value, and then you would choose for the second. So I'm just gonna programmatically go through this. Your first your first slope is going to be the slope at 1, right? So you're going to evaluate the point and this the point at 1, get the slope at 1.
Yep.
And then set the next y value to be the old y value plus 0.1 times the slope. Is that what you intended?
Looks like it.
That seems like a reasonable thing to do.
So if we end, now it throws a fit. Nope. Okay, it did it automatically. Good. Excellent. I do have to go back and actually say, no, we need to, what was it? Oh, right. First of all, we need to say that y of 1 is going to be -2. Right, so the rest of that is just wrong anyway. Sorry. Y equals zeros. 1, but no, 1 by 21. Right, and then y of 1 is 2. Okay. And then we say, let's do generally, if we do delta t is equal to 0.1 now, then we can go back through our code and say, okay, for I going from 1 to 21, we said our f of I is going to be this thing, which I don't have any arguments against. Not changing it. And then our y is going to be this, and again we can change this now to generally be delta t, like that. And then that was it, right? Just end. Yep. Okay. So here we got our values. Yeah, payload too large. We get our final y values here when everything's all filled out. I really also should have muted the output for those, but whatever, it's fine. We see here that we get a -2 for the first one, of course, that was given. -1.92 for the second, and a -1.83 for the third. That is not what we got, is it?
That is. I have my automated thing here. It matches.
Oh, okay, yep.
Mine does match. Cool. Negative, and then 1 point. Yeah, these all look great.
Yeah, and it does match my actual notes, so that's good.
Yep.
So one of the questions would be like, how good is this, Zach, compared to your, picture version? How
so
accurate?
My picture version, it's basically on point. I mean, I can see very little error from what you have and what I have here. Like it's within, I'd say, 10 to the -4.
That's really good.
We're pretty good.
How far out does it go before it starts deviating noticeably?
On mine?
Yeah.
Gosh, I'm out to x equals 30, and we're doing fine.
Okay.
So just for the record, this one converged quite nicely. That's not always universally true, mind you.
Also true.
But but for this particular function, it actually is pretty good.
Yeah. So, right. 4 minus t times 1 over x. It wants x in this one. Keep forgetting that. Plus y squared. Right, so if we put 0, -2 as our solution here, right, this ends up getting us a fairly nice solution curve. Looks like this. And yeah, also like you said, this does converge, so it makes it much easier to work with. If it is a divergent system where this thing just goes off to infinity, then we could be deviating fairly quickly. With a t value of 0.1, that's actually pretty reasonable, and I wouldn't expect somebody to do this by hand for any amount of time. Going from 0 to 1 would be enough of a pain. You saw just doing the first 2 calculations took us a good 3 to 5 minutes. So
just to emphasize, you might want to show what happens with like an h equals 1 or delta t equals 1. Just to show what happens. I don't know if you can.
Oh yeah,
but
this is easy.
But just to show.
So we go in
hey,
here.
Benvox. Welcome.
We say delta t equals 1. right? And then let's go back through the iteration again. So we say for I going from here to here, we got f, which I'm going to mute this now. F is going to be this, and y is going to be this, mute. And then just end. Calculate. All right, so it re-upped. You can see up there, it kind of blinked, which told me that it re-evaluated those terms. So if we go in and say, what is y then? And it's going to give us the whole vector. Again, 22 units long. Right, so our first one goes from -2 to -1.2. So that used to be -1.92 when we were 10 times more accurate going through like that. Also, now this is still using the larger numbers, so this goes like further out, I think. But nonetheless, this is like 1 comma -1.2. So at 1, it should have been basically 0 if it wasn't actually 0. No. Right, at 1 it should have been like -0.1-ish. So instead we get a 1 comma -1.2. It's really far off. Right, and then 2 comma 0.488. In the last set we had 2 comma, and that's that last number, 1.469. So yeah, it's way off. If we were to graph this, right, what are the t values? I suppose we should get that. Right. Oh no, I messed up. Right, because t is not that anymore. Let's see. 1 to 5. Hell, just 1 to 21. It's fine. And we got to run it through this whole thing again. Right. There we go. Okay, so -0 comma -2, 1 comma -0.8, which actually is not awful, but it's still not right.
But I guess what I wanted to show here is that there's oscillatory behavior. You can see your jump from negative to positive behavior, which really shouldn't happen. So yeah. Our slopes are horrible approximations in some sense, and I guess I just wanted to make sure you get a chance to see that.
Right, because in this you can also see like these values as we go 1, 2, 3, 4 like that, our y values are deviating above and below where it looks like an asymptote should exist. Somewhere around y equals 1, right?
Yep.
Anyway, yeah. Thank you for bringing that up.
And when I meant convergence, that's the kind of convergence I was talking about. Not so much the divergence to infinity, but the being able to jump up and down, having a your solution, your approximate solution, actually somewhat resembles the analytic solution.
Sorry, I was just checking something out to make sure. Okay.
And fun fact, this is what was claimed in Hidden Figures, if I'm not mistaken. Euler's method was the thing that was used that Katherine Johnson. Or no, it was Catherine. It was who was it? Catherine Goebel. That's the name. So it was Johnson, but then changed to Goebel if I remember correctly. And yeah, so this is a fun pop culture fact. It's a good film, by the way. Highly recommend.
Yeah, still haven't seen it, but it's been on my list. I've been meaning to do it for a while.
There was a way to do if there was a legit way to do a watch party, I would do it with you. So like we would do it. Like if you have Disney Plus, I think we can do it.
Yes, I do. That's true.
So we may have to do like a Disney Plus thing where I can, you and I can co-stream the movie together, and it's a good movie. You should watch it.
Definitely. All right, so in addition to Euler's method, we've got several other ones to go through. There is the backward Euler. Which is not particularly nice. It is actually what I wrote over there. I typed it out earlier because I didn't want to have to type it out again. So what we're going to do is assume that all instances of our t and our y in the slope are from the next value. So that's a little weird. If we use the exact same f function, so we're not going to change anything really, and in fact we're going to keep almost the exact same Euler's method formula. So it's still going to be y sub n plus 1 is going to be equal to y sub n plus delta t times f of, here's where it changes. So instead of this being t and y sub n, what we're going to do is say that this is going to be t sub n plus 1, y sub n plus 1. Which is really weird. But nonetheless, if we want to do, again, just like 1 by hand, right, y sub 1 is going to be equal to, here we got y sub 0 was negative 2, plus 0.1 times our f here was 4 minus t sub n plus 1 is known. So we know that this is going to be 0.1 as our next t value. And then we do times y sub, y sub 1. And then put that over 1 plus y sub 1 squared. So this becomes a little weird, because now we've got instances of y sub 1 scattered throughout the whole thing. How do you feel about it, Zach?
Oof.
You have seen this before, right? Because I don't know.
I've seen it. I don't use it very at all. Like, to be blunt, I don't use this. I've seen it at one point when I took mathematical biology, but we didn't play with this much. We mostly are going to go towards Runge-Kutta, which is like the more mainstay one. But
yep.
But like this one, I think was mentioned in passing.
Yep.
I was like, oh, gross.
Yeah. When I started teaching this, I was like, oh, that's kind of really messed up, and I was like, I can't even wrap my head around it half the time. And finally, when I did get more comfortable with it and get actually doing some of these, then I was like, wow, I'm really glad that we're automating this. And then
very, very yes.
When I was prepping this here, I was like, wait, Does anyone else actually teach this?
Yeah, I mean it's taught, but like it's not as far as I've never actually seen it used in practice. That doesn't mean it isn't, but I've just never seen it. And if you and I have never seen it, that's a sample of two. So,
But at the same
but
time,
I just
like,
haven't.
you've taught DE before, right?
Right. I mean, we didn't focus too much on these methods when I did it. Like, I think we talked about Euler's method briefly, but not significantly. I tended to focus on analytic solutions for mine, but I mentioned it in passing, saying, "Hey, you can approximate these, and in practice, sometimes that's what you actually have to do, especially for nonlinear things." I don't know if you saw Two Curbs' message, by the way.
I have not.
Obi.
Sorry.
So Two Curbs had an interesting question. I responded to it in chat, but I'm curious if you have a different answer. At least my experience is what I gave. Does differential equations have some fundamental theorem like the fundamental theorem of calculus? And I don't know if you have a different answer than mine. I talked about the existence uniqueness theorem in some sense is like a fundamental theorem, but like, do you have a different answer you would give?
Probably not, in the sense that, like, that is the go-to to at least say, like, differential equations is a valid field. Like, hey, this actually is a, here's our, like, number one reason for studying differential equations. They exist.
Well, and I mean, the fact that they exist allows us to pull off this method of Euler's method, or, Runge-Kutta and so on. That's sort of what allows us to say that this is even a good idea. Yeah. 1.6, not 1.96, I think Fembox is saying.
Yep. 100%. So glad I have people.
They save me. I mean, everybody in chat saves me every single time, I swear. It's quite fun to... It's good that we have everybody here, because I love having... It's the peer review I need, right?
Yep. All right, so from this, you notice that this is going to be a cubic equation, so I'm not solving that. Right, so what we can do...
Come on now, depress the cubic and do the whole thing Penn Center taught us, right?
I don't think I was there for that one.
Oh, you weren't there for... Okay. Check the VOD, it's good. Because you can depress the cubic and make it a solvable cubic and so on.
But, good news, if we do this as VPA solve, we could say that we've got now y cubed plus 2 y... that's not going to work. Hang on. Gotta put in the multipliers because otherwise they yell at me. And actually this may yell at me anyway. Nope. Y equals @sims. I think is the right way to do it. Plus 1.01 times y minus 1.6.
Interesting.
Think.
So as you're doing this, I learned something new as I was looking at the backward method.
Plus 1.
Because I wanted to know more about this, and I was like, why would anyone want to... Apparently, fun fact, according to Wolfram Math World, the Euler forward method is less stable than the backward method. I didn't actually know the backward method was stable at all, but that's interesting. It's unconditionally stable, it says.
No, that should work. In theory. Oh.
So fun facts.
Does that do it? Nope. Ugh. did I do? Nope, not that. Nuts. Apologies, everybody. Gotta remember how to solve things, because I did that, but there was something else that I changed. Oh, it's just sim space y, I think. Symbolic package. A. And go. A. There we go.
EG's.
Okay. So, and this goes out to some ridiculous number of decimal places, which is, you know, well beyond the precision that we're even allowed to have, given that t is supposed to be 0.1. Right? Like, it's going to a very large number of decimal places. So we're good out to, like, what, 6 or 8 probably most of the time. Just as mathematicians, I do encourage people to keep all the decimal places, even if they're not going to actually end up using it. But at any rate, we're just going to iterate. We would iterate this over and over and over again, and just come back and say, you know, let's plug this. The result we get here, which again is y1 is equal to negative 1.909821264. More stuff after that. Right, so that's our 0.1 comma negative 1.9098. And that's just going to, like I said, when we start doing this over and over again and iterating, we're going to end up with numbers that are going to be fairly similar but slightly different from the y values we had up above. So if we find our y values from above, we had a negative 1.92 instead of negative 1.9098. Negative 1.83. The next one down the list that I have is negative 1.8076. So again, our hundredths value is off by a bit, but and then negative 1.6908. So we're about 4/100ths off. Negative 1.555664. So we're about 6/100ths off. And then last one, negative 1.396. So we're getting close to a full 10th off. And that's by 0.12345. Well, which one's more accurate, Zach?
Good question. I didn't see the coefficients. Femvox was asking if there's one real solution. I'm curious here if there should. I don't know the discriminant on that.
Right, 1, 2, 1.01, and 1.6.
Mm-hmm. So I didn't see that.
I am fairly certain that there is one real solution and 2 imaginary or complex.
Okay. Yeah, I just don't know. So I'm gonna verify.
Yeah, when I was doing this beforehand, I did not do VPA solve. I just did solve, and it gave me all 3 in symbolic, which meant that it gave me the exact, which it's not nice. So if we do that, that should work. There we go. Yep.
Yeah, I think we're okay because I'm coming up with one real 2 complex when I solved it.
Yep. And of course, plot it, right? If you just graph it, you can see it just goes through once.
Cool.
So this is the exact value rendered in ASCII.
Yeah, like the backwards Euler Femvox, I'll be honest, I didn't learn it well. I've only seen it. And I'll point you to Math World here, because Math World seems to suggest that it's unconditionally stable, this method. And I'm curious about that. I don't know exactly why that is. In practice, I don't see this being used very often. I just don't hear about it very much. I just heard about it once, which usually means to me that it's not used very often. But I don't know. I'll direct you there.
Okay. So the Heun formula is another one that was one of those, like, did everybody else actually learn this, or this one named after Karl Heun, German mathematician from...
So this one is a variation on Runge-Kutta. As I'm looking it up, I've never heard it by that name.
Mm-hmm.
It calls it, I mean, Wikipedia calls it a two-stage Runge-Kutta method, but that's more, it's a midpoint method, it looks like.
Yeah.
It's an improved Euler.
So I tie this in to what my students have learned in Calc 2. I don't know if you can see it. But here we're doing the whole, like, finding the average of two values. And there's somewhere in Calc 2 specifically that all the students do, through trying to find a numerical way to solve integrals, have to take...
You mean trapezoids?
That's it. Yep. So it might not be like 100% analog, but at the same time, it's really similar when you start thinking about, like, what is this doing? Well, here we're taking the average of two particular slopes, two particular function values, and then using that as part of in this case, it's not a summation that we're doing. It's going to be trying to find a stepped differential equation slope. So we're coming in and we're saying, okay, well, we're doing this whole, like, you know, follow the path like this, and then at every stage we're basically taking our, as you said, take the Euler's method of, like, well, one of them went this way and one of them went this way. And we're trying to find the average between those things, and it ends up working out to the particular direction that's selected. That's not there, is it, though? That is the current slope and the next slope according to Euler's method. So like both of these end up averaging and feeding back. All right, what do we think? It's probably in the wrong place again.
I think we're. Or you mean like the average idea that you were talking about?
Yeah.
I think we're okay.
Yeah, okay. So, again, this last bit here, as Zach said, it is Euler's method embedded within this other part of the Heun formula.
So basically, you're making an intermediate value based on Euler's method. Then you take that new method, average it with the you take the new point that you made, the new y point as input, average that with the Euler's method point, and then multiply it by h.
Slopes.
Those are slopes. Yeah, that's right. So slopes at ti, yi, right? Like so, you have
Yep.
your Euler method one, and then you have your your Euler method slope. And so sorry. Let me rephrase. This is hard to say out loud. I haven't like had to say this one out loud before. But you take the slope you would have calculated with Euler's method, right?
Yep.
And then you would have you take the slope with the projection using Euler's method and average those. And that becomes the new slope it becomes your true new y value. If that makes sense.
Yep.
I don't know if I said that in the clearest way, but that's the basic idea, I think.
Right, so we take the Euler's method slope at t0, and then find that projected point, take that slope, and then average those two slopes, and start over from the beginning with that new slope, and say that's where we're going.
Right.
Hopefully I also said that correctly.
So here's the thing. This is basically a two-stage Runge-Kutta method.
Yes.
And so I'm more used to using Runge-Kutta with four things, but with it's like the standard algorithm in MATLAB is RK4.
Yep.
And that's a weighted average, but basically applying this principle 4 times, where you project out 3 times, use those new y values, and then weight the average of those outputs of the slopes. Which is really bizarre, and that doesn't sound like it makes sense at all. But you're basically doing a number of projections and weighting the average of those projections and saying, okay, what's the slope that's reasonably in between all of those?
And currently, Runge-Kutta is like the gold standard.
And specifically, I've seen RK4, like with a 4th degree Runge-Kutta. But anyway.
Yeah, we'll just put a 4 there. So like you could do this with just about anything you wanted. You could even go out to some ridiculous number like RK8, but I say ridiculous. But at the same time, you're starting to sacrifice computing power for accuracy that you don't even need, precision that you don't even need. We're going to see when we do Runge-Kutta here, it converges to like the correct solution 99 times out of 100 super fast. So like even RK4, it's just that's good enough. You're probably never going to need more calculation than that unless you're in a particular situation which is going to require it. I don't know if you would agree with that statement.
I think that's accurate. Like I think that's you're doing far more than it's necessary if you go past 4.
For what little you're going to get in return.
Right. But like you were saying, the gold standard is a 4th order Runge-Kutta approximation. That's pretty good.
Right, and if we look at how the weighted average is structured, then again, this is going to be, hey, this is reminiscent of something else from Calc 2.
This is Simpson's rule.
Yeah, I mean, it looks pretty much identical. The only difference is, I don't know if when you increase the order, if you get the alternating coefficients like you do in Simpsons.
That's a good question. I actually don't know the answer to that.
Because it could all be 2's in the middle, in which case it's more like trapezoid. But
yeah,
either way.
Yeah, I actually don't know. And I'm looking at the generalization of Runge-Kutta, and I'm not seeing. I don't know. Good question.
Something I probably should have looked up for today, but you know, whatever.
Ooh, Simpsons. That's true. 142424241.
Yep. Okay, so where, this is where it gets fun, right? K1 is just our Euler's, nope. Nope, never mind. We're just taking the same slope approximation as we did with Euler's formula. So K1 is just the slope starting from wherever we are. K2 is going to be the slope from the halfway point, t sub n plus delta t over 2. So at this point, we're only going over 0.05 rather than 0.1 if we're going to use this. Right, and then our y value that we're going to get is Euler's form, or Euler's method. So here we get y sub n plus delta t over 2 multiplied by k sub 1. Then k sub 3 is going to take our f of t sub n plus delta t over 2. So again, same halfway point in terms of our t direction, but then our y value is going to be y sub n plus now delta t over 2 times our k sub 2 version. So we're using Euler's formula, but now using the slope that we just found from K2 down here for K3. And then we do it one more time for K4. It's going to be f of t sub n plus delta t. So now we go all the way over. Alright, now we go all the way over, and we use y sub n plus, this is now just delta t times, again, we're just going all the way over with our y value, taking that line and then going all the way out to our next t value. So the full delta t times k3. So, like, this is something that I definitely do not want to do by hand. It's easy enough to do, like, once, but generally speaking, you just want to plug this into a computer and tell it, go for it, man. Have fun. Alright, so in order to do Runge-Kutta for this one, reconnect. Right, this is where it gets fun. So, we've got to say, first off, what is f? F is undefined. Cool. So, this is started over on us. Oh, right. You can see over on the left, the vars is completely clear except for answer. Alright, delta t right now is going to be set for 0.1. Again, we're getting the same values we did before. T is going to be equal to, let's go from 0, oops, bracket, 0, use delta t as our increment, getting smart now, see? And then we're going to go to 100 times delta t. And mute that result. Alright, so we're going 100 spaces. In this case, we're going out to 10. So, much further than we had before. It'll be fine. Okay. So, this is going to be for I going from 1 to 100 delta t. Need a multiplication symbol in there. Always, always. And technically we need plus 1 on there. Or, no, 100. Got caught by another ad. Alrighty. We should be back now. Apologies for that. Yeah, I didn't do the pre-roll stuff, so oh well. And we didn't take our mid-session break. Oh well. Okay, so for I going from 1 to 100 delta t, then what we're going to do is we're going to say that k1 is going to be equal to, we didn't define f. Ah, man. That's fine. F of I. We need multi-input, don't we? Oh, it's T sub. Jeez. Was that Dark Side of the Moon? Or are you just getting blank? Alright, I think we're going to have to... I mean, we could do this out, but we'll just say we've got our k. We want this to be 4 minus t of I, the current value, multiplied by y, the current value, over 1 plus y of I squared. Okay. We want K2 to be 4 minus T sub I plus 0.5 times delta T. That's not it. Nope. Outside of. Pull the T value and then add half of delta T. And then we want y of okay, so y sub n, and then that's this thing, plus 0.5 times delta t times k1 over same deal, 0.5 times delta t times k1. K3 is going to be the exact same, except we're going to change all instances of K1 to K2. And then K4 is almost going to be the same, but here we're going to just add all delta t into the t value. And delta t is going to be multiplied by K3, not a half. And y of I is going to be equal to nope, plus 1. Iterate. It's going to be y of I plus delta t times parentheses over 6. This is k1 plus 2 times k2 plus 2 times k3 plus k4. And don't tell me what that is until the very end. And end. In theory. Right. So all of this is undefined at the moment. That's fine. We need... y is zeros 1 by 100 times delta t. Right, there's no e in zeros according to this. We have to find zeros. Alright, that one. With the anyway. Right, and nope, I don't want that. I want y of 1 to be equal to -2. And I want t's already there. T, just make sure all those. Cool. Alright. Here we go. So now we go and step through all this stuff again. Hopefully I got it right this time. So 4. K1 is going to be this. K2 is going to be this. K3 is going to be this. No! Okay. K4 is going to be this.
Rip.
Oh no.
I'm sorry.
Well,
Oh no.
hopefully that is fine. And y is going to be this, and then end. Woo. What's y? I think that might be right, despite the disconnection and whatever else.
So those numbers look reminiscent of what we had before, in our last.
Also true. Yep, I just need to check
those.
the...
Those are I was going to say that makes me think of the numbers that we had before when we did this with Euler's method.
Yep.
Which tells me that we're in the right ballpark.
Alright, so I got -1.91522. Looks good.
Yep.
And -1.8205. So that's a bit off, but that could also... noticed... I'm going to say that that's probably also a potential hand calculation error, because I didn't that's me doing it by hand on my notes. So the graph I saw, so mine had a graph of Euler solution, and what's interesting is that the Euler solution was off by a bit towards the beginning. I think the early x values all off initially by more than at the end. And so I wonder if that's what's happening here, is that this negative, that you're off by a little bit, that might be because Euler's method just slowly and, I don't know, maybe not. I'm willing to entertain the idea. Yeah.
That's what I'm wondering, is it's just a speed of convergence issue.
I don't think so. So I think Runge-Kutta converges the best because it's taking all these averages and saying over this next step that we're going to take, these are all of the different things that are going to be averaged together to fall into this. Right. I think the issue with Euler is if there's any sort of second derivative change, which is large, it's not going to reflect it.
Right. Whereas, I guess what I'm saying is that that Runge-Kutta I would expect to be more accurate. And
yes.
I put more faith in that one than I would in Euler's method. That's what I was trying to communicate, and I guess if I didn't say that, it's on me.
No, I think that's right. And there's also a potential mismatch that I made between... No, that's probably fine. I mean, there's a little bit of a mismatch, definitely. 'Cause I said, oh no, okay. I just threw in two different values here because I was looking at y going from y being made of zeros from 1 index 1 through index 100 delta t, whereas the t vector was from 0 up to the number 100 delta t, which is 10, incremented by 0.1 by our delta t. So I only gave y 10 positions to work with. So that's only going from 0 to 1. Which we said, from 0 to 1, we should expect this to be negative 0.1. Right, negative 0.16 seemed reasonable for something we were doing. Yeah. So, negative 0.16, reasonable approximation, negative 0.14. So yeah, this is only going for the first 10 or 11 indices. We've still got all this other stuff to play with, all these here, which I didn't actually use. That's fine. Your mileage may vary and all that stuff. So naturally, if we increase the number, or decrease our delta t, increase the number of positions we're using, increase the number of steps that the computer takes, we should expect that all of our methods are going to be more and more accurate, and eventually get an approximation that's unreasonably close to whatever the actual solution should be. Again, it's going to take more computer time in order to get the more accurate results, so we've got to balance what your computer time is going to be versus how accurate you actually want the result to be. Zach, any thoughts?
I have nothing right now.
Okay. I have one more.
I mean,
yep.
No, go ahead. No, I didn't have
That's fine.
anything really to say.
So I have one more like fun differential equation to just check out the slope field for. But while I do that, if you had something else.
Not right now. I'm just sort of. What's this other function? The x squared over plus 3x over, or sorry, x squared plus 3x plus 2, all divided by y minus 2. That's the one. Okay.
So this is actually a function that's on the cover of the 10th edition of Boyson de Prima. So I stared at it quite a bit. But one of the things that you can notice here is that, like, as we change our initial value, we get some really weird stuff going on over on the left. Which I think kind of brings back what you were saying earlier, where we have this, in this case, right, it is also oscillatory behavior that's going on here, and like, why should that occur?
Yeah, well, you've got this. You've got a vertical slope field there. I think that's part of the issue. You're having some undefined slopes.
Yep.
Yeah, and Femvox is pointing it out too. X equals -2 and x equals -1 seem like problem points. Trying to see why that could be. Oh, I see what you're saying. At x equals -2, and like I see. So you have a center there.
Yep.
You have your direction field is circulating -2, 2. I think that's something different, Femvox. It's I'm talking more about the slope field itself. Generally has vertical slopes around -4 and -3.5 x values. True, you could solve this one by hand.
So what Femvox is pointing out is that we have what we would probably call either singular points or equilibrium points, or like there's a whole bunch of different words you can use depending on the context and like what each one actually does at those locations. I'm not actually sure 100% right now, without actually doing some minor calculations, like what is happening at each of those individual points. It could be like the Lagrange points in orbit around Earth and the Sun and whatever other, multi-body systems exist. Gravity kind of plays up a little bit when you start getting toward these equilibrium points. I never remember which ones are which, but the one that JWST is currently orbiting around is an unstable equilibrium point. So that Lagrange point requires somewhat regular alteration of orbit in order to make sure that it remains in orbit around that particular location. It is not a stable equilibrium point where kind of like everything just sinks into it. Which also is kind of a good thing, because if you put a satellite at a stable equilibrium point, then like dust and debris and, minor rocks and things like that could end up gathering there and bonking into your satellites. That might be a bad thing. But, so yeah, James Webb is currently around an unstable equilibrium point where everything's just going to fall away from it, given a slight nudge in any particular direction. We are going to talk more about equilibrium points and the behaviors around them, and like how do you find them, and what the mathematical behaviors are at and around those particular points in the next unit. So when we start talking about linear algebra and systems of differential equations, that's when we start talking about like all that interplay. So that is what Femvox is talking about there. And Zach, what you were talking about is as we're moving to the left, right, we end up with this y equals 2, where all of our slopes are undefined. Right? Every single slope all the way along y equals 2 is going to be vertical due to the fact that dy dx is dividing by 0. So what we get is kind of the same thing as what happened on the other one, where we're making our like delta t step and then hopping over that line into the y is greater than 2 region, where if we continue to the left, the slope will then go back down, or it'll be positive. So because we're going to the left, it's going to go back down again, and then jump over the line again, and then our slopes are back to being negative. So when we step left, we go back up, and then we go back down, and then we go back up, and it just keeps doing this dance where we jump back and forth. There's one here where it actually does, apparently, that can't be right. Yeah, that right there can't be right. But most likely what happened is it went back down and up in such short order that it's not even reflected on this or something. I don't even know how it got from there to there, but either way, the computer may also not be rendering all of the t-steps that we have here. even though it's calculated all of them. So I'm not sure exactly what the code is behind GeoGebra, but you know, there's all sorts of cool stuff that could be happening. Yeah, so anywhere near y equals 2, we have that problem. And again, we can change our individual values. We can try to get really close to -2, 2. You notice that here, when we land at this position, we can't go anywhere. Like, there is no delta x, there is no delta y. They're both going to be 0, so we're just kind of stuck here at an indeterminate point, right? Indeterminate behavior. And then we go off like this. Let's change the color. Of course. Boo. I thought it would change the color of the line, but alas. Alright, and we get the same thing going on over here on the other side too. Depending on what we pick, there's all sorts of weird stuff going on. And again, if we go really close to this one, we have the same problem over on this side. So we have to be careful with what exactly we're picking. And again, -1, 2 is indeterminate. Can't do anything with it. It's just a singular point by itself, 0 divided by 0. All right. Anybody have any particular questions from here?
I'm particularly fascinated in these this picture here, by the way, because it reminds me of the dynamical systems stuff I love. So this will be exciting to talk about this in some detail if we can.
There was a particular solution for this, no pun intended, that looked something roughly like this. Now, if you're actually graphing this, right, the actual solution for this does come around and back down and under. It doesn't have to be a function in x. And that's really the problem with this one right here, is that our f prime becomes divided by 0, so we get this problem. And we're just assuming that all of this stuff should be functions. So therefore, like this thing where it kind of loops back on itself just should not happen, right? Why would that ever happen? I actually went to a talk in undergrad where one of the guys was working on like a particular version of this. I forget exactly what this is called too, but is it an elliptic curve of some kind or another?
That sounds correct. That sounds correct. I can't verify 100%, but I believe that's right.
Yeah. So he was doing some sort of research on this, elliptic curve. I think he in particular was trying to do elliptic curve encryption. And some of it has to do with the fact that you have like a point on the upper half and a point on the lower half, and it has some interplay. I can't remember exactly what it was. It's really sad. But I mean, it's been 20 years since I was at this talk, so oof. But there was some really cool stuff that happens with elliptic curves like this. And like I said, you can do elliptic curve ciphers with things like this. I don't know how to do it, but there's all sorts of cool areas, including cryptography, obviously, which deal with these particular kinds of curves. All right. Other questions? Comments? Oops. Nope. Hey, Rendu. Good evening. Nice to see you. And everybody else, thank you very much for coming in. Richard Cuttingware. All right, so let's drop in everybody's information one more time, because we cannot do any of this without all of you who came in here all the way back in the day and said like, hey, this is a cool stream, you ought to join up with us and come over here and talk with us and have all sorts of fun. So thank you to our list of other streamers. These are the Math Chads. Don Does Math. Zach, E to the 2i Pi, has been here tonight with me. Penn Center is, again, the person who has hosted this class and is also hosting his own complex variables class on Tuesdays and Thursdays. Ian Stuckey, who has also been in here fairly often. Myself, Obi-Wan Pez at NSimplex Pachinko, Danny Highway, and Dr. Gold at Actual Education. And we also want to throw specifically Zach and Penn Center. Those are the Discord and Twitch links to their pages. So if you have anything you want to check out there, feel free to have a look around and come see the rest of us and come have an awesome time, right? I think we're probably going to wrap up class, and we will likely still stick around here just for a couple of little math things. I still have to do more lifting for major finger, and and we will be back tomorrow night for our regular math session. So this is just homework help. Anything you want to talk about, let me know, and we'll do some interesting stuff. And on Wednesday, we will be back for more differential equations, where we will begin talking about, this is actually somewhat getting into the dynamical systems that Zach was talking about. Our initial point of contact here is going to be a freshwater lake with an intake stream that has pollution coming into it, but is also flowing out of it on the opposite side. So how does this lake's water get affected by some sort of pollutant coming in? This type of system is representative of a near infinite number of different scenarios that could occur anywhere out there in the real world. This is one of the most interesting parts of differential equations, because when you start doing it, you start realizing just all of the different places that it could apply to. And I mean, it's just mind-blowing. Yep, mixing problems, but it's not just mixing problems, right? It's predator-prey, it's, half a dozen other things that I could think of off the top of my head were I in my right mind. All right, Zach, do you have anything else tonight?
I was going to say the applications here, right? Newton's law of cooling, right? Which is mixing problems, but it goes farther than that, because some of the papers I read papers in mathematical biology, and diffusion is everywhere. Every population ever is diffusive.
Yep.
So if you know anything about what's called the heat equation, that is literally a mathematical biologist's playground, an assumption for everything that a population will diffuse across a region, if you will. There's so many like dynamical systems are all over the place
Mm-hmm.
in like planetary modeling. I mean, there's actually a fun. I don't know if you'll talk about it, but there's a fun example called the chaotic water wheel that you ought to look into. Do you know about this?
I
The
think I
water
saw
wheel that
somebody
has,
build it.
yeah, like there's a fun little exercise about nonlinear systems that is it's fun, but I just don't know where you're gonna go with. If you're gonna go
So
there or not.
I do actually
It's a
want
fun.
to touch on like the three-body problem.
Okay.
I don't know if I'm going to like show the proof. Probably not, because goodness, I'm going to be the only one who's interested. That the three-body problem is unsolvable. But yeah, I think probably not actually show the proof, but at least do like a couple of the basic calculations to look at like what would it take to solve this. Yeah, there was actually I'll let you go first, but anything you want to plug?
Go check out Simplex. Go check out Penn Center, running classes, and I'll be doing Infinite Series in September. So if you want to come do like a thing with Infinite Series, get excited for that. I'll get more information coming in the coming months.
Where would you say the prerequisite is for that?
I'm trying to minimize those prerequisites.
That is awesome.
What I'm probably going to do, I'm going to try and minimize the amount of calculus we need. I'm actually thinking in August, late August, early September, we're going to give you a little rundown of what I expect anyway. So but I'm going to minimize the prerequisites, and I'm hoping to put it at a point where if you've only heard of derivatives and integrals at a very level, you should be okay.
Mm-hmm.
Limits, derivatives, integrals. You should have a very I would even say calculus 1 might be too much, right? I want to do even better than that, but I'm still figuring out what the prerequisites should look like. So I don't want to commit to anything yet. But if you're excited about that kind of stuff, know that we're doing that interactive. We're going to have like a whole. I'll give more details. It's going to run basically the same way we did last time with real analysis. Just get excited. I mean, it's going to be so fun, and I've got some fun things in store coming at the end of July. So I will plug that, but I'm not going to tell you what those things are yet. I've been programming like mad. Let's just say that. So I'm excited for some upgrades.
Anybody who is interested in some of the, I hate to use the word, but lower level stuff, things that are perhaps a little bit less calculus involved, I would like to run my pre-calculus class and or Calc 1 class, probably end of this year into next year. So we'll see how that all lines up with everybody else. I don't want to step on, stream at the same time as too many other people, but
yeah, that's a conversation that it's just it's going to be interesting seeing how these classes. It seems like this is becoming a more common occurrence. I don't know if Penn Center's plans or any of the other streamers, if there's going to be any other need for that. We'll see.
Yep. Alrighty. Have a good night, Zach.
Yeah, good night. Thank you.
What are you planning to be on next?
I'm going to be on tonight doing some stuff, and I'm still figuring out which topic, because it was a tie when people voted. So I will be on later, I'm still trying to decide what that will look like.
Woo!
So I was looking at the list of topics, and I'm like, all those sound interesting. And I'm not sure which one we're going to talk about yet. So I'm still deciding. We'll be in touch.
Alrighty.
Yeah. And Fogel, it's good to see you. And I know that in just a few minutes, Dr. Gold will be on. So if you want to go raid, unless you had somebody else in mind.
Not particularly, so.
Okay. So if we wait, I don't know how much time it's
probably 5-10 minutes, something like that.
Yeah, 5-10 minutes.
I could fill time. That's easy.
I'm looking at the server, actual education server. I don't see anything yet, but we shall see.
Alrighty. Well, have a good night, Zach. Or, well,
You
see you in a
too.
bit.
I was gonna say we'll see. I'll be here. I've got to defend my title for Dr. Gold's
Yeah,
SAT prep.
yeah, definitely.
I gotta defend it because apparently I've been outdone a few times, and
Ooh.
I feel ashamed. Like when I misread the question, or sometimes the inputs are a little.
Yeah,
So
that's true. And also, I had both of my computers up at one point, and I
so,
typed in the answer over on this one. I'm like, oh no.
yeah, Laz is super fast. I have to say.
I
I'm
type in
impressed.
$A space, and I have my fingers
Oh,
on all four keys.
oh, you know it. You know it. Like I am ready. I have the same thing. I'm ready. I'm getting excited for tonight because I want to defend my not championship, but it's like sort of a back and forth right
Yeah,
now.
yeah.
So
Gotta get your points.
gotta get my points. Gotta get my bond coin. So anyway, that's my competitive side coming out. You're seeing that. You want to see that competitive side come out? I will be in chat, attempting to regain my title.
Awesome. All right.
Okay.
We'll see you over there.
Yep. See ya.
Have fun. Alrighty. So, if anyone has any other questions about other math stuff, it doesn't have to be about differential equations. I'm going to open up the floor to anything that anybody wants to talk about. And then, yeah, we'll head over to Dr. Gold's shortly. Probably in about, like we said, 10 minutes-ish. We'll see how things go. What's my least favorite differential equation? The one I can't solve. You want a tier list? Oh no. Let's see. So, I mean, like, I don't know. Gonna have to, like, do some actual research to figure stuff out. Spread of an epidemic. That's just, yeah. That's my least favorite right now. This differential equation never helped anyone. F tier, yeah. One of my friends, I was gonna tell two stories. One of my friend's sons, who is also sort of my friend, he's 25, 30 by now, but he and his girlfriend, I believe they're married now, living in Germany. She's German. They both got a job at the same school, so I mean, like, perfect. And they're both mathematicians. They spend most of their time, like, in front of their computers, and then they have whiteboards that they just, like, work on together all the time. It's really quite impressive. That's how you feel about exact equations. It's just so contrived. But he was he was trying to figure out what research topic to do, and he said, I want to do a research topic that is so esoteric that no one is ever going to find an application for it. And he found something and was like, this is what I want to do. And he talked with his advisor, and his advisor's like, yep, that looks like something that nobody's ever going to figure out what to do. And within 3 months, somebody had said, citation. Here's an application for that thing. And he's like, damn it, man, come on. It was great. And then, speaking of non-linear differential equations, like you all had done early, yes, trying to build useless things, come on now. speaking of nonlinear differential equations, I had a gentleman who worked at the applied physics lab at Johns Hopkins, and he was way long retired when I met him. But I was when I went there, I was clean shaven. This was when I went to my church. I was completely clean shaven, and this guy got to know us, went and talked and all sorts of stuff, and he found out that I was a math teacher and that I had taken, or I was prepping to take partial and nonlinear differential equations and do my master's in applied math. And let's see, it was 3 months later after we met him, I grew my beard out for the winter because, you know, it's cold occasionally in Maryland. And he puts his arm around my spouse and says, "Now I just have to say that your husband has a glorious beard." And she told me about this, and I was just like, Dave, it's an interesting choice of words. Job opportunity at Johns Hopkins for math education. Oh, man. I also don't have any plans of doing a master's, but yeah, or a doctorate, but this might be a good one for you there. So months later, and in fact it was probably a couple of years later, we were talking about some other stuff and like the projects that he had worked on at the applied physics lab, and it was really cool listening to, like, you know, all of this. I think he was aerospace specifically, and he was 80 in 2015-ish. So, like, you know, you go 40 years back, that's 1975, you go another 10, right? 10 to 15, he's 25, finishing his doctorate. I think he had a doctorate in, like, 1964. So, he might very well have worked on, at least in theory, some of the stuff at Goddard. I was just like, man, that's super cool that, like, you know, he probably had some opportunity to work on, you know, Cold War era technology, and possibly some stuff that went to space and satellites and, like, all this cool stuff. So we were talking, and he said, you know, Obi, obviously he didn't know that name, you know, Obi, you're gonna solve the three-body problem. And I'm just like, get out. It's like, Dave, you know for a fact that that is not solvable. It's like, dude, it would have to be somebody like Newton-esque who would have to invent a brand new branch of, like, calculus in order to be able to figure out nonlinear differential equations in any sort of way. Like, that's not me. If you've talked to me for any amount of time, you know that that's not me. But oh my goodness, he was a great guy. He ended up passing in 2020, 2021, somewhere in there. And his wife, who was a very quiet, soft-spoken lady, like, made it another, I don't know, 6 months, maybe a year. But it was one of those where, like, the two of them were pretty much inseparable, so the two of them passed basically within a year of each other. It wasn't surprising. Hashtag relationship goals, maybe? No. What are my least favorite differential equations? I gotta think, like, what are my least favorite to solve, right? Because, like, by hand. Or teach. What's my least favorite section to teach? I mean, it might be, actually, some of the earlier stuff with, like, Laplace transforms. Like, it's not, by itself, it's not too bad. But the problem is that you've just got so much, like, so much stuff to get through in your head in order to understand Laplace transforms. It's a lot less intuitive when you see Laplace transforms, at least for the first few times, few dozen, 100 even. Yeah, this stuff's kind of nasty. If you put, like, 1 plus x squared at the front of a second order, those get kind of gross. Because, I mean, as you can see here, right, this requires a power series to... it may not actually require a power series, I shouldn't say that, but this one at least, like, kind of looks like it needs it, and that's the expectation at the moment. Method of Frobenius. There were some interesting things with, like, the Bernoulli's differential equations. But you've got, like, your regular second order differential equation, but then the other side has is it y to the r, I think? Or no. We'll find it. That's going to take a minute. This is an 800-page book. 1 of 8. Okay. Yeah, there we go. Yep, first order. So y prime plus p of x y is equal to f of x times y to the r. So when r is equal to 0, we do our typical differential equations as we saw earlier. But then the problem is that we have, if r is not 0, right, then we're looking at this and saying, we're going to solve we do the same, oh my goodness. Variation of parameters. Hey. We haven't talked about that yet. Yeah, we did that stuff. Yeah, u prime is equal to f of x over y1. We get the complementary equation. So actually, this is something that's going to come up later. I don't need it to be that big. Right, we get y prime plus p of xy is equal to f of x. When we found solutions to this, it was now we can't quite do that in we can do it in general, but I don't like to because I don't know 100% if right, this is going to be e to the integral of p of x dx times all that stuff. Is going to be the derivative of p, nope, e to the that stuff. The integral of p of x dx times y. Right? That is equal to f of x, which means that y is going to be equal to, we take the integral of both sides, it's the integral of f of x dx, and the other side we throw the e to the other side, it becomes negative integral p of x dx in the exponent. So that's a little weird, but in general, right, this is going to be our solution for that. Oh, e. I forgot e on the other side again. Here's the integral of p of x dx times f of x dx. So, kind of nasty, but it does allow us to solve this in general, so that's pretty awesome. Right, so it's saying that the complementary equation was going to be y prime plus p of x y equals 0. So all this stuff, the same stuff applies. It's e to the integral, gets multiplied to all terms. It becomes the derivative of the product rule. And so like e to the integral of p of x dx times y is going to be equal to c, some constant. And then we shift this over, y is going to be equal to c times e to the negative integral p of x dx. So rather than being just a constant in the complementary equation, right, we get all of this stuff here. Right, so that stuff is not strictly a constant. So when you're doing Bernoulli equations, we're saying that the that just flew. Okay. saying that the other side right? So y1 is going to be e to the x is a solution of the complementary equation. So we look for solutions of the form y is equal to u, which is some other function of x, times the complementary. So this is actually a tactic that we're going to use in second order as well. So over here, if we're kind of going about trying to solve this, so u of x, which we already know from the other one is integral of e to the integral of p of x dx times f of x dx. Right, so we already know. We already know this thing. Ayya. So we're going to take another 40-second break here while we wait for the ads to complete. Because again, we didn't actually take any time because I thought we were already going to be in Dr. Gold's at this point. Whoops. And thank you for anybody who is subscribed to the channel. Awesomeness. And thanks to anybody who is new here. Means a lot that you came. Means a lot that you stayed. And we're back. All right. So sorry about that. We do have, right? If we assume that u of x is going to be this stuff over here, right? If it's just generally f of x, a function of x that we have, then et voila, we can say, yeah, well, we know that our u of x is going to be the integral of e to the integral p of x dx times f of x dx. But then what about Bernoulli equations? So for that, you've got y prime plus p of xy is equal to f of x times y to the r. So yeah, that's a little weird. So we already know that y equals e to the negative integral p of x dx is a solution to the complementary equation. to assume that y1 or y sub c or anything else like that, right? Oftentimes we'll do something like that. Say, okay, well this is a complementary solution, but then we're going to expand, or homogeneous solution is what we usually call it. Assume that y, the general solution for this, is going to be a function of x, and it's going to be u of x multiplied by y sub c. Okay. So we go with y prime, that's going to be a power rule. Nope, sorry, product rule. So u prime y plus u y prime plus p times uy c in all these cases is equal to f of x times u to the r y sub c to the r I know that tune. Piano romance? Something else. Right, okay. Right. So we have u times the quantity y sub c prime plus p y sub c. And over here, this is u prime y sub c plus that. And over on the other side is f of x times u to the r y sub c to the r. Okay, we said earlier the complementary equation, right, is y sub c prime plus p times y sub c is equal to 0. Right? Because by definition it's the complementary equation, so that's going to end up getting us a 0 value because up top, like we said, y prime plus pu times y is equal to 0 is the complementary equation. We know what the solution is. We call it y sub c. Okay, so that leads us to u prime y sub c is equal to f of x times u of x to the r times y sub c to the r. Move u to the r and move y sub c. This gets us u prime over u to the r. That's easily solvable. Is equal to f of x times y sub c to the r minus 1. Okay. Not entirely solvable, but that's fine. looked better than it did before. When we take the integral of both sides with respect to x, right, u prime over u to the r, it's going to be over u to the r minus 1, right, times 1 over the new exponent, is equal to, and then here this isn't going to be well, not going to be generally solvable, but might be useful in some cases. And then can we just repeat that until we run out of exponents on y? That'd be kind of nice. Might be disgusting. Transforming nonlinear equations into separable ones. Yeah. Oh, right, you could just make it a root then, no matter what the exponent actually is. Right, u to the r minus 1 is going to be equal to 1 over, r minus 1 times the integral of f of x times y sub c raised to the r minus 1 dx. And then u is going to be equal to the r minus 1th root of that stuff. Minus 1 times the integral of f of x times y sub c to the r minus 1 dx. Might still be doable. But that does mean that, right, y as a general answer is going to be y complementary multiplied by u, the thing we just found here, 1 over y minus y, r minus 1 times the integral of f of x, y sub c to the r minus 1 dx. And like, all things considered, that's actually not that bad. I mean, you might not be able to find the integral, but at least it exists. Alright, let's just hop to like a random Bernoulli equation that's not a Bernoulli equation. Let's hop to a random Bernoulli equation. Right, so like 47 here. y prime minus 4y is equal to y squared e to the negative x plus 2e to the x. Okay, complementary minus 4yc is equal to 0 is, right, so y sub c is going to be e to the negative 4x. Nope, positive 4. So we have to subtract 4 of them in order for that to happen. We could do it out long, but okay, so y is going to be equal to u times y sub c. So we go back to the original. U prime y sub c plus u times y sub c prime. We could shortcut this realistically. Minus 4 y sub c. U times y sub c. Is equal to u squared y sub c squared e to the negative x plus 2e to the x. That's not equal to there. That's just going to be a colon. Right here, this stuff is going to be 0 again. Because again, y sub c prime minus 4 y sub c is going to be 0. We just factor out the u's from both of those terms. So that's gone. Again, we don't have something quite separable this time. E to the x. How do you make that separable? Do we just say that that's going to be... you can't get all the terms out. This might be something where it's like, you can't actually do it, but here we can find something close. Okay, so here, these end up being binomials or something similar. Oh. Transformation of, it's nonlinear into separable. It's close enough. Okay, yeah, right. We can still get it in terms of U, potentially. I think I was just focused too much on it. It's fine. Yeah, we can't do this. At least not with what it's trying to do. Right, U squared times y sub c e to the negative x plus 2e to the x. Oh, over. Removed a y from that one, so 2 over y. Right, we're trying to get the u term to the opposite side. Oh, really? All of that stuff together. Oh boy. Maybe. Okay, so this is going to be y sub c e to the negative x times the quantity u squared times 1 plus, that's not separable. So if we're factoring that out, this is going to be e to the 2x over y sub c squared. It's equal to u prime. Hum. Yeah, that's a problem. Oh well. Okay. We are going to go and see Dr. Gold, because he is now on. So we're going to raid on over. Thank you everybody for hanging out, and we will be back tomorrow for regular math office hours. Come on in with questions if you've got anything. That is far too many people I'm not following. And we'll be back on Wednesday for the next part in differential equations, the class. So, we'll head on over. Thank you very much for coming, and I hope everybody has a good couple of days. Oh. And we'll see you next time. We're also here on Friday for gaming type stuff if anyone is interested. That's not going to be me. Here, we'll throw this in as a raid call. This is like the first time I've ever done it, so yay, let's do it. Anyway, hope everybody has a good couple of days. I will see you either tomorrow, Wednesday, or Friday. I hope. And we will catch you then. My name is Obi-Wan Piz. This is N Simplex Pachinko, and we will see you next time.